In the previous video, we talked about using the law of sines when we knew two angles and a side, either angle side angle, where you had two angles and the side included between those two angles, or side angle angle when you had two angles and one of the non-included sides. In this video, though, we're going to be talking about a case where we know two sides and a non-included angle. By way of reminding you, and don't really have to memorize this, two sides and an included angle, side angle side, that's going to be the law of cosines. We'll talk about that one later. So right now we're going to be talking about two sides and a non-included angle. So for example, if I have these two sides and this non-included angle, that's an example of side-side angle. Going in order, side, side, angle. I have a side, and the next thing I have is a side, and the next thing I have is an angle. Now, normally, when I'm setting up a problem that I know is going to use either the law of sines or the law of cosines, which we haven't talked about yet, I always set my triangles up using the exact same format. Now, I did not do that in the previous video, primarily because I was given a triangle and I just kind of picked some sides and labeled them, picked some angles and gave them names. But in this case, I'm going to start labeling my triangles always this way. A is going to go here, B is going to be this combination, and C will be the angle at the top, and the side C will be the side at the bottom. And the reason for that is that I can look at this now and decide if this is a side-side angle case where I need to make some adjustments. We call this the ambiguous case because there are potentially two different answers here. And it's going to be up to us to decide, first of all, how many answers there are, and if there is more than one answer, what both of those answers might be. Now I've drawn this triangle so that it looks like the triangles on the previous slide or in the previous video. But let's take a look at what might happen if I had an angle and two sides, and I won't draw in this other side here yet, but I've drawn in this bottom side just so we have it for reference. I'll call that C. I'll call this side B. And for now, let's assume that this is a 30-degree angle. And let's also assume that B equals 10. Now, what if this side over here was 4? That would be A, right? A equals 4. Well, it turns out that if A equals 4, it's not going to be long enough to become the third side of a triangle here. Remember that the sine of 30 degrees is a half. That means the side opposite it here has to be 1 to 2. The ratio has to be 1 to 2 at the hypotenuse. So this side would have to be 5 in order for this sine of 30 to be 1/2. If it's only 4, it's not long enough. It can't make this right triangle. So this side isn't long enough to reach the bottom side, side C. So there's one case at least where there's no triangle formed. We'll call that case 1, no triangle. Case 2, let me erase my hanging chad there. And if I bring this all the way down so that it just barely touches, but does in fact touch the bottom side, and that means that has to be a right angle. It also means that since the sine of 30 is a half, that this side has to be 5. So let's change that to A equals 5. And now I have case 2. 1 triangle. There's a third case. I just realized I haven't really labeled my triangle, so I'm going to go ahead and do that now. This angle here is angle B, and I have angle A, angle B, angle C, and I always measure A at the bottom left, B at the bottom right, and C at the top. I always label my triangles that way. And then I have side A is here, side B and side C. And in this case, side C is actually this guy right here. And I don't have the rest of this. Right, that's all too much. That's okay, that's just this particular case. In this case, angle B is 90 degrees. So if your third side, your second side actually, your side A here, if your side A is long enough to reach the bottom, it's long enough but not too long, then that forces this to be a right angle. So in addition to knowing in this case that we have one triangle, we know that it's a right triangle. Now I've written over my case 1, so let's call this case 2. And I'll very quickly recreate case 1 here. We had a side B, angle A, and side A wasn't long enough. So if we're starting with a 30-degree angle and a known side B, and we're given another side, that side can either be not long enough, just long enough, or as in this third case, too long. Here's my side B, which I'm going to make 10. And I'll make this my 30-degree angle. And then if my third side is too long, I'm going to have to think differently. I've been told that the length of this side B is 10, and I will be told that the length of this side over here maybe is 7, for example. But I can't leave it hanging off the end there because now it's forming a triangle. Let me use a different color. It's forming a triangle that has a side of 10 and a side we don't know and a side, but that third side is not 7. I need to use the entire length 7 as part of my triangle. So I'm going to need to redraw this. Here's my side B. Oops, wrong color pen. Here's my side B. Here's the part of side C. Now I don't know how much of side C I'm going to need yet, so I'm just drawing a line that's a bit too long. And then my side 7, shorter than 10, but it has to come down and somehow meet this third side down here. So I'm going to bring it down like this. And that's going to make this 7, this side 10, and this side we don't know. This is angle A, this will be angle B, and here's angle C. Now that I know what it looks like, I can erase the extra part of C that I don't need, side C. All right, so well, that all looks good, right? And now we can use the law of sines. And it's true, we can use the law of sines. I forgot to put my 30-degree angle in there. We have a sine and an angle opposite each other whose values we know. We know the measurements of these two opposites. We have a third piece of information, and the piece opposite that is angle B. We don't know that, but we can figure it out. So let's use the law of sines on this, and then I'll come back and show you why this is not the only solution. Case 3, it turns out, is going to be 2 triangles. So let's figure out this first triangle, and then we'll talk about what makes this the ambiguous case. Very quickly, the law of sines says sine A over length A equals sine B over length B. I know sine A, it's sine of 30 degrees. I know length A, it's 7. I don't know B, so I'm just going to have to write this as the sine of angle B for now, over length B, which is 10. Now, I've used the law of sines a couple of times before, but I've always been looking for a side. This time I'm looking for an angle. The process is the same. Here I'm going to get 10 times the sine of 30 degrees equals 7 times the sine of B. Now, this time I'm looking for sine of B so that I can solve for B, so I'm going to leave this here and divide both sides by 7. And that tells me then that the sine of angle B is equal to, let's cancel those 7s, 10 times the sine of 30 degrees over 7. Well, that's 10 times, do you remember? It's a half over 7. Half of 10 is 5, so I get 5 over 7. But that's the sine of B. To find B, let me do this a little bit differently from how I was going to do it. What I currently have is this. The sine of B equals 5 over 7. So let's take the arcsine of both sides. Give myself enough space here. All right, so I get B equals whatever the sine inverse of 5 over 7 is, and I don't know. So I'm going to have to do that on my calculator. When I do, I get that B is approximately 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . 45.5847 . All right, so I have found angle B. I have a measurement for angle B. That's this one here. I was given a measurement for angle A. It was 30 degrees. And with that, I can now find angle C. Once I have angle C, I can use the law of sines again to find side C, just like I did in the previous video. The thing is, we're not done here because there's another way that this triangle can be formed with an angle of 30 and a side of 10 and a side of 7. Let me show you. First of all, I'll erase my work from before and make a copy of my diagram because I can't move my diagram. And then I'm going to erase some of my details here, but not all of them. I'm going to erase this 7. And actually, I think that's all I need to erase. I'm going to erase the size of angle B because it's actually going to turn out to be incorrect for our next problem. And so I'm going to leave this copy over here, and I'm going to work on this copy. Now, remember that we said the side of length A, the length of side A, that's this one here, had to be 7, but we didn't say exactly where it had to sit. We found one position for it. I'm going to make that a dotted line. And that's still valid, but there's another place that it could go, and that's here. It's still 7. It's just in. It's like I swung it over to another place where its bottom could hit the end of side C. And so if you imagine that this is a bar swinging on a pivot up here, but this is a steel plate, then this bar can swing up, but when it swings down, it hits the floor here. If we swing it up and all the way over, then when we swing it down, it hits the floor here. So it can sit in either of those two positions. If it has to have a length of side 7, then there are 2 places that it could hit the floor, but there are only 2 places. So now that we look at the situation we have here, you can still see the first triangle we found, and we knew that B had a measure of about 45.6 degrees. Now we're looking for a different triangle. Now we're looking for this triangle. Let me highlight it. So if I want to find the sides and the other angles of this triangle, then I need to use the law of sines again. Let me relabel my side C, side A, that's 7. I have an angle and a side opposite each other and a third piece of information, so I should be able to find angle B, right? But I did that already. I plugged into my calculator the sine inverse of 5 over 7, or was it 7 over 5? No, it was 5 over 7, the sine inverse of 5 over 7, and that's what gave me this 45 degrees. So if I, just by drawing my triangle this way, if I then try to use the law of sines directly, I'm still going to get an angle of 45 degrees, and that's this angle over here, 45.6 degrees. And that's not right, right? This angle here, this one right here, and this one right here are clearly different sizes. In fact, we're going to call this one B prime because it's a second angle B that can occur in the situation where you have a 30-degree angle and 2 non-included sides, well, 2 sides 10 and 7 in a non-included angle of 30 degrees. So how do we figure out what this angle is? Well, it turns out to be pretty easy if you just think about it a little bit logically. Here's the deal. Let's use green no, I'll use blue as a highlighter. Remember, this side is 7. That's set in the problem. It'll be given to you. Side A is 7, or the side opposite angle A is 7. But this was a 7 as well. That means they're the same length. That means that this is an isosceles triangle, and I'll use pink for this. Nope, not a highlighter, sorry, bear with me. These 2 angles, these 2 pink angles, are equal. These 2 sides are equal, so these 2 angles are equal. Right now, I am looking at this triangle. Not a right triangle, but I'm using a fact from geometry that if the 2 sides of a triangle, if 2 sides of a triangle are the same, then the 2 angles opposite those 2 sides must also be equal. Okay, if these 2 angles are equal, then this angle is 45.6 degrees. I know how big it is. Well, if I know how big this angle is, I can figure out how big this angle is, because together they make 180 degrees, right? So whatever this angle is, it's 180 minus this one. Let's do that arithmetic. I still have my full 45.5846914 showing in my calculator. So I'm going to type 180 minus second answer, and that pulls as much accuracy from the calculator, even more than that is showing on the screen, as much accuracy as possible. And when I hit enter, I get that 180 minus 45.6 is 134. Oops, wrong color of pen. I want yellow for now. 134.4153 degrees. I've checked, my calculator is in degrees. I'm doing all of this in degrees because the problem was given to me in degrees. Okay. Now, I now know the size of this angle. It's about 46 degrees. That means this angle is also about 46 degrees because this is an isosceles triangle. And because these two angles have to add, this is a straight line here. So these two angles have to add up to 180. Since I know this one, subtract that from 180 and I get 134.4 degrees. So now I have this triangle, which was the first one that I found. I was given an angle of 30. I was told the side opposite it was 7 and another side was 10. I used the law of sines to find the second angle, the one opposite the other side. I've got this matched pair of values, but I had a piece missing here, and I used the law of sines to find that value. Once I had B, I could use that to find C. Once I had C, I could use the law of sines again to find side C. And I have this triangle. Let me highlight it a little bit differently. In order to find this triangle, I first had to recognize that it was possible for it to exist. I still have angle 30, side opposite angle 30 is 7, another side is 10, and I can use the law of sines here, but when I set it up, algebraically, I'm going to get the sine of 30 over 7 equals the sine of 10 over the unknown angle. And when I do that on my calculator, I'm going to get the same value for B. So I can't just change the triangle and do the same arithmetic or do the same mathematics and expect it to give me a different answer. I have to recognize, first of all, that this side 7 here, when compared to or when combined with this side 7 here, makes an isosceles triangle. These two angles are the same, so now I can use that to find angle B prime. If this was our first angle B, this was our secondary angle B, and we just call it B prime. Just using a little bit of arithmetic and a little bit of information from geometry, I can determine that the second angle B is 134.4 degrees. Now that I know that, I can find my third angle. 30 plus 134.4 plus something equals 180. And once I know that, I can use the law of sines again to find side C. Side C is going to be shorter this time because angle B is bigger. So this is the case in which I had two completely different possible triangles. This is my case 3. Case 1 was no triangle exists because one of the sides you're given is too short. Case 2, that was this one here, case 1. Case 2 is where that side that you're given is not too short, but neither is it too long. It just comes down and perfectly touches the bottom of the triangle down here, hits the steel plate in a perfectly vertical line. In that case, there's only one triangle, and it's a right triangle. In case 3, we have two different triangles, and this is the tricky one. The thing is, you won't know until you really get started whether the side is long enough, too long, or just right. So let's do another problem. In fact, let's do a couple more where we investigate what those options are and how you might come to make those decisions. Okay, I decided that this was a really good opportunity to look at an application as well. Let me read through this and then we'll talk through what some of our options are. A tree grows vertically on a steep hill that forms a 20-degree angle with the horizontal. To ensure that the tree does not fall down, a 54-foot long cable will be run from a 55-foot high branch on the tree to a point on the ground uphill from the tree. How far from the base of the tree will the cable need to be anchored? Well, I don't know about you, but I like to see a picture. Let's say that this is my hillside. And actually, 20 degrees is a lot shallower than that. So let me try that again. We have a hillside that's forming a 20-degree angle with the horizontal. So we have 20 degrees. And we have a tree growing vertically on that hillside. At a point 55 feet high, let's call that 55, a branch 55 foot high, we're going to take a 54-foot cable and run it, 54 feet, and run it so that it anchors into the ground. All right, now this kind of looks like I don't have enough information. I have two sides of a triangle, but I don't have any of the angles, but I can figure out what the angle is. If you imagine that the tree is growing down here instead, it's still on this slope, but it's growing vertically. So that tells you that if this is 20 degrees, and we assume that the tree is growing vertically, that means it's forming a 90-degree angle. That means the remaining angle is 70 degrees. If we just slide that up here, imagining that the horizontal is here, let me just go ahead and draw that in. If we imagine that the horizontal is here, then by a property of geometry, we know if this angle is 20, then this angle is also 20. And noticing that if this angle is 20, and this is a right angle, then this angle right here must be 70 degrees. So this is a really good example of a situation in which you were given enough information to solve the problem, but not directly. We had to figure out what this angle was before we could start working on the problem. But now I do have enough information. If I label my triangle the way I like to do, I have this angle A here, that makes this side A here. And this would be angle B down here, which means this is side B. That leaves angle C and side C. Now, let's see, what was I asked for? How far from the base of the tree will the cable need to be anchored? Well, the base of the tree is here, and my cable is anchored up here. So I'm actually looking for side C in this problem. Let's go ahead and highlight that. This is the piece of information I actually want. All right, let's just use the law of sines and see what happens. The angle is 70 degrees. The side opposite is 54 degrees. So I have a known ratio. I have sine of 70 degrees over 54. And I know that that equals sine of C over C, but I don't know either of these angles. So I'm going to have to go in where I do know another piece of information, and that's the B information. So I'm going to have to start here with the sine of B over 55. Ultimately, I'd like to have the sine of C over C, and I'll get there, but I don't have either of those right now, so I need to figure out what angle B is, and I can use that to find angle C, and eventually use the law of sines again to find side C. So let's go ahead and do this problem. If I cross multiply, I get 55 times the sine of 70 degrees equals 54 times the sine of B. Dividing both sides by 54, I get sine of B is approximately, now I'll cancel my 54s here. What I'm going to be doing is this arithmetic on my calculator. I get 0.9571. I actually get 0.957094336. I don't need to record all of that on paper, but I am going to leave it in my calculator. I'm going to leave it on the screen because the next operation that I'm going to do is going to use this value, and I want to use it in its most accurate form. My calculator will remember not only 0.957094336, but several more decimal places, even more beyond that. So I'll leave that in the screen in the calculator. And now what I'm going to do is take the sine inverse of both sides of this approximate equality. I don't have room to write that down here, but that's what I'm doing. The sine inverse of sine of B is B. And the sine inverse, I'm going to type second sine, and that'll put the sine inverse on my calculator. Then I'm going to type second answer to type the answer from the previous line in. That's that 0.95709 right? Several decimal places. Now I'll hit enter, and I get 73.1554. I'm working with an angle here, so this is in degrees. I know it's in degrees because the problem was given to me in degrees. I had to find the 70-degree angle first, but even that is in degrees. So my answer to angle B is also in degrees. Now that I know B, I have two angles, I can find the third. Angle C is going to be equal to 180 degrees minus 70 degrees minus 73.1554, or more accurately, 73.15542287, and even more, because I still have it in my calculator. So I'm going to type 180 minus 70 minus second answer. When I hit enter, I get 36.8446. So now I have angle B and angle C. But what I wanted was side C. So since what I have is one pair of things opposite and a known opposite from an unknown, and this is the unknown I want, I can use the law of sines again. The sine of 70 over 54 is equal to the sine of angle C, which I now know to be about 36.8446. Just realized I forgot my degrees down here, over the unknown side C that I want. Once again, as I do this computation, when I get ready to do the arithmetic, I'm going to be using the value that's currently displayed on the screen in my calculator rather than typing this in, because it's more accurate. I get C, I'm doing it a little backwards this time, C times the sine of 70 degrees equals 54 times the sine of 36.8 degrees, running out of room there. Divide both sides by sine of 70. Cancel those, and I get that C, side C, is approximately equal to 54 times sine of, 54 times sine of second answer, because I now have that angle, but it's more accurate in my screen. It's 36.9, 36.8. 54 times sine of second answer divided by sine of 70. And I get 34.4590. 34.4590 feet. And it appears that that's the answer to my question. I was asked how far up the hill, or how far from the base of the tree will the cable need to be anchored? And the answer appears to be 34.4590 feet. Appears to be. But there's another answer. What I'm going to do now is redraw this triangle in a slightly different configuration. So here's my angle. This was angle A. It's down here, and I've kind of rotated the triangle so that instead of being up a hill like this, it looks like it's on a horizontal. This is my angle B, this is my side B, but instead of being vertical, it's slanted because the whole thing has been rotated down this way. My other side was given as 54. We were told it had to be a 54-foot cable, so there's my 54. Now watch what happens when I look at this possibility instead. Let me try drawing that again. This triangle's somewhat exaggerated, but I hope anyway, you'll get the point that if that is 54, it's also not very accurate. It doesn't look like an isosceles triangle, does it? But if that's also 54, right here, then this is an isosceles triangle, which means these two angles are the same. Since this angle, B, is about 73 degrees, this angle is also about 73 degrees. That means this angle, let's see, I have to do the arithmetic. It's 180 minus, going back up to a place where I have the exact value, or a much more accurate decimal anyway, and I get 106.8446. So it's 106.9 degrees. Now I have 55 across from 106, 107, and I have 70 degrees across from 54. So I can use the fact that I have two angles to find a third. I can use that to find this, and then I can use the law of sines again to find my new C value, the value of the length of the base of the smaller triangle here. We could call that C prime in the same way that we've called the new angle B prime. All right, so now what I'm going to do is figure out what that third angle is. I know this one's 70 degrees. I know this one right here is 106.9 degrees. So using my calculator and using that scrolling property that I used before, I'm going to calculate 180 degrees minus 70 degrees minus about 106.9 degrees, but I'm going to use the value in my calculator so that it's more accurate. So let's do that. 180 minus 70, of course that's 110, but I'm lazy, minus, now I'm going to scroll up until I get to the last instance of the answer that was 106 point something, and that's 106.8445771. My calculator is using a much more accurate answer than 106.9, and when I hit enter, I get 3.1554229, so I'll use 3.1554. So this angle up here is pretty small, 3.1554 degrees. And now I can use the law of sines again to find C prime. I know that the sine of 70 over 54 is equal to the sine of 3.1, that's 3.2, if I'm rounding accurately, degrees, over C prime, which means that C prime times the sine of 70 equals 54 times the sine of 3.2. Now, again, I'm just using this as a record-keeping device. The actual answer I will use when I do this arithmetic, when I do this computation, is the one on my calculator screen because it's more accurate. I know I'm saying that a lot, but it's really important. Divide both sides by the sine of 70. And I get C prime is approximately equal to 54 times the sine of second answer divided by sine of 70. And that gives me 3.1632. 3.1632. So this is actually a second possible answer to how far away the cable has to be anchored from the base of the tree. Now, why is it important that we find two answers here? Well, depending on the scenario, depending on exactly which situation you're looking at, depending on, I guess, a lot of other potential factors, we found two answers here. Let me draw this one in first, actually. And I think I'm going to do it with different colors, too. All the stuff I've highlighted in green goes with the possibility that the cable gets anchored here. And all the stuff I've highlighted in yellow corresponds to the yellow highlighted cable. And the question I might ask you is, which one is going to be more effective? Is it more effective to anchor the tree? Because you're trying to keep this tree from falling down, right? Is it going to be more effective to anchor it farther up the hill? Or is it going to be more effective to anchor it closer to the base of the tree? Well, that will depend on what's going on in the field as well. Are you trying to prevent it from blowing over in a wind that's going to come down the hill like this? Or are you trying to prevent it from blowing down or falling down because of some force that might be coming down from the top or pushing up in this direction? Well, that's a physics question, so we're not going to try to answer that here. But my point is that depending on the situation, either of these answers might be more appropriate in the field. So it's important to be able to figure out both answers, to know that there are two possibilities and find them both. Now, as far as homework exercises go, you might just be asked to find the triangle or the parts of the triangle in the obtuse case. For example, this second value here, the second angle B and the second side C. Even though you're only finding one triangle, you're only solving for one triangle, you're still going to need to find the first triangle, right? You can't figure out what this angle is if you don't know what this angle is. And you won't know what this angle is until you know what this angle is. So to find this second angle, this B prime, you're still going to have to find B. Once you have B prime, you'll be able to figure out what this angle here is. I'll call that angle C. Oops, wrong color pen. Angle C prime, as opposed to little c side C prime. So even if I ask you just to find the second case, the obtuse triangle here, you're still going to need to find the at least one of the parts. Let's see, do you need to find the other part? You don't necessarily need to find the long side C, but you'll definitely need to find angle B in order to find angle B prime. You'll need angle B prime to find angle C prime, and you'll need angle C prime to find side C prime. So even though you're only finding one triangle, this triangle, you'll still need to do the work of finding parts of the first triangle. So that's the law of sines, and this video specifically has been about the ambiguous case. The ambiguous case is the case where you know two sides and a non-included angle. The other cases we've talked about in the law of sines, in the previous video, we talked about the two angles and one side. And both of those cases can be dealt with, whether that's the included angle or not, just using the law of sines without worrying about a second possible solution. The ambiguous case is the case where you have two sides and a non-included angle. In the next video, we're going to be talking about a different strategy, the law of cosines. That covers two final cases, two sides and an included angle, side, angle, side, and all three sides, side, side, side. If you go back to the first screen at the beginning of the previous video, the one that was just called the law of sines, you'll see that the labels I gave to the 6 different scenarios, the second one was something we couldn't deal with at all. If you have all 3 angles of a triangle, that's a lot of different triangles you can build that way. But the first and last cases were the ones that dealt with the law of cosines. That's what we're going to be doing next.